Right, guys, make a start now. Questions? On top of material in the lectures, labs going well. So I'm going to do the lab tomorrow with you guys. Tutorials.
So what are the properties for the objective function in regards to the extreme estimator? Because it seems like you can create any objective function depending on your model. But what properties do you use to decide if the objective function is actually function?
Anything, something that makes sense. It can be least squares. It can be least deviations from moments.
Is there any property from?
Yeah, anything that makes sense, right? Really, but this is a conceptually very important question. Because depending on what objective function you have, your consistency comes from the objective function. Really, right? If you set some strange objective function, you are not going to get consistency, right? It has to have some link with what you're trying to do. Okay, it can be deviation from moments, it can be deviation from strange moments, like maximum likelihood. That's in that the maximum likelihood can be looked upon as a GMM as well, but very different kinds of moments there. Okay, so it depends on the context. So you can have any objective function and you will get a different estimator. You can have penalized objective functions, just a standard least squares together with a penalty. You guys have seen the lasso, right? So it can be really anything. Okay, it depends on the context, depends on what you are looking to do, and you are going to get a different estimator in each case. If your objective function is reasonably well specified in relation to the problem that you are looking at, you get consistency. That is where consistency comes from. And if they are of a particular nature, and that is what we are doing here, if they are of the least squares nature, they are of the GMM nature, they are of the ML nature, then additional large sample properties come, like efficiency, like asymptotic normality, right? And there are only a few of them, so that is why we are covering them individually, okay? Only a few known ones, let us say. But remember, for the lasso, asymptotic properties were shown only in the last 5-7 years. So it's, for strange objective functions, it's actually difficult. Okay. Anything else? Okay. So today we'll start closing down different parts. We'll start closing down. We'll close down everything, right? So kind of bring the house down. Okay, so that's the idea. So we'll see how we go about this. But we'll start with panel data, then go into identification, specification tests. Some of you guys have asked me questions about maximum likelihood, so I'm going to cover a little bit of that again, go over it again, all right? And then, depending on how much time we have and so on and so forth, maybe some exam type questions and so on. Right? So that's the plan. Okay. Right. So panel data, what do we know so far? So panel data regression model is very simple. YIT is equal to some beta 0 plus beta 1. Okay, let me just write it this way. X1IT plus beta k xkit plus an error term for us panel data is longitudinal, right? So you select n units right at the start and you try to follow the same units over time. Okay? So if you have balanced data then n equal to 1 to n and t equal to 1 to t. What is the central problem here? Well, the central problem here is that the same unit is observed over repeated periods in time. So if your model was not perfect, there were some omitted variables which were being carried by this unit, then they get repeated over time. So you do not have IID setting, right? So IID is out. Okay, however, as we have been seeing, rather than that being a limitation, that is actually a strength. Because suppose we could write down this error term in the error components form, alpha I plus UIT. I don't remember what notations we are following. Yeah, eta IT is it? Okay. Suppose we could write it in this form, then we can incorporate any factor that is not time varying, any unobserved heterogeneity that is not time varying into this alpha I. And then we can deal with it in a better way. So what do we mean by that? Well, maybe we can do first differencing. Okay, then what happens? You have del YIT is equal to, well, beta 1 del X1 IT, okay, plus beta K del XK IT plus del eta IT. See that the alpha is gone. That's nice. However, if we were interested in the effect of some variables which are not time varying, then this is not going to work. For example, institutions are very stable, right? For example, gender, race, so on and so forth, they are also gone. As we have seen, education also goes away. Experience, likewise, in the wage equation. So there are some downsides to it, but the main feature of this is that we have got rid of the alpha I. Is that the only way we can do it? No, we can do fixed effects as well. Fixed effects or least squares dummy variables, where instead of taking differences, we take this guy. Where's the sound going to go? Where these guys are what? Well, YIT, for example, is YIT with 2 dots minus Y bar I. Okay, once again, by doing this transformation, we find that we can get rid of the alpha I. What about random effects? What do we do in random effects? Well, we do not quite do y dot dot, but we do something like y tilde it, which is equal to yit minus some theta y bar I, where theta is between 0 and 1. 0 and 1. Okay, so theta has to do with the relative importance of the two error components. Okay, and then we can do GLS, we can do maximum likelihood, so on and so forth. So these are all ways to handle this unobserved error component, right? The unobserved time invariant heterogeneity, okay, often also called fixed effects, but that is, we think, very poor terminology. All right. Okay, so far so good, right? So you guys understand that. What we have been trying to do now is endow our model with a little bit of dynamics. Okay, so how do we do that? Well, we include a lag dependent variable on the right hand side. Very simple. Okay? And the same error components here. So everything is just as before. However, we now start having problems. Okay, so let us see what this is. So basically the problem is something called nickel bias. Okay, and it comes from Steve Nickel, 1981, and almost immediately afterwards there were, well, estimates started coming out. But anyway, so what is the nature of nickel bias? Well, what nickel bias highlights is the fact that when you are using the within transformation, this guy here, or quasi-demeaning, this guy here, right, then the y becomes endogenous. Okay? Why? Well, that is fairly easy to see, right? So what are you doing here? You are taking this transformation of the y. On the right hand side, you are going to have a similar transformation of your lagged y, right? And you are going to have a similar transformation of your errors, but then your transformed errors and this guy here, the demeaned yt minus 1, they are going to get correlated. Okay? So yi, well, I've got the notations the other way as well here. Okay, so let me just correct this. What are we calling that? We are calling that y tilde. This one we are calling double dot. Okay. Right. So, when we do this transformation, this is our yi bar, okay? And then this guy is guaranteed to have all the errors mixed up in there, right? And the transform errors are also guaranteed to have all the errors. So this guy will be correlated with this guy. That's the problem. Okay? The correlation does not come from the contemporaneous errors, right? It comes from the other errors. In each term, there is this yi bar, which is including all the different y's and therefore all the different errors. Right? So the degree of correlation is of the order 1 by t, right? Because this guy has a averaging transformation there. Okay? So we have an endogeneity problem here, but that endogeneity problem should go away as t goes to infinity, right? Okay. But the central idea is that you cannot use fixed effects or random effects. Because the transformation in either case makes this guy or that guy endogenous. The good news is that this bias is of order 1 by t. So in a large t asymptotic setting, when n is fixed and t goes to infinity, nickel bias disappears asymptotically. Okay? And here's the intuition behind it. You guys will be able to write it down and see this exactly. Okay? How big is this problem? So this thing does not disappear very fast. Of course, it disappears as t goes to infinity, but can be quite large. For t equal to 10, okay, so which in a panel setting is not a small panel, right? T equal to 10 is something that one would struggle to have, right, in a longitudinal panel, right? Going to the same household 10 times and collecting data on them, you know, so if it were your household, you would probably throw them away unless you were an economics student, right? So it's not possible, literally impossible to do it. Okay? So, and if the true lambda was 0.5, the p-lim of the FE estimator is about 0.33. So which way does this go, the bias? Well, for the laggard dependent term, the bias is an attenuation bias, right? So it brings the estimate down towards 0. Okay, so asymptotically badly biased downwards. So we need something else. What is that something else? So what else can we do here? So if we had this kind of a structure, and somehow we were suspecting that this alpha I may actually be correlated with the x's. So what would you do? What are the things that, what are the transformations that we have learned? Fixed effects doesn't work here. What was the other one? First differencing. All right. So let us see whether first differencing works. Why might first differencing have a better chance of working? A priori. So what were the moment conditions for first differencing? So for first differencing, we did not need the strict exogeneity conditions, right? Okay? So after a few lags, the correlation is 0 there, right? Well, you do not need to assume, you do not need to assume that the correlation is 0 beyond one lag and one lead. Right? So maybe there's a better chance of it working. So let us see how this works. All right, so again, back to our usual model. Let's now start with first differencing. Del YIT is this guy, del YIT minus 1, and this guy, right? So this is this, and this is this. Unfortunately, these two are correlated as well. Okay? There's YIT minus 1 here, and there's eta IT minus 1 here. Those two are correlated. Yeah? That is straightforward. If you write this equation for the period t minus 1, you can see in a straightforward way that this, you know, this eta IT minus 1 will be here, and YIT minus 1 will be there, so the two will be correlated. Okay? So there is a correlation. But suppose we could find an instrument for this. So what can be an instrument? Can yit minus 2 be an instrument? Yit minus 2 is obviously correlated with this guy, right? Yit minus 2 is correlated with eta it minus 2, but eta it minus 2 is not here, right? So that can work. Alright, so we'll be taking this idea forward. So we'll try to do GMM by finding instruments for this guy. Okay. So we have done first differences to eliminate the alpha I. This is our equation. Anderson-Chow suggested using IVs, using lagged levels as excluded instruments for S greater than or equal to 2y. Well, first of all, we have already seen that yit minus 2 will work. Yit minus 3 will work as well in principle. Why? Because yit minus 3 should be related to yit minus 2. Why? Because of this model, right? So it should be correlated. Okay, if your lambda is not 0, then it is correlated. Is it correlated with the errors? No, it's not correlated with the errors. So yit minus 3 can work as well, and so on. So you can use several instruments here. So lagged levels, yit minus s are valid instruments if s greater than or equal to 2, and here there is a discussion of some of these. However, there is a problem as well. What is the correlation of this guy with yit minus 2? That is minus sigma square y, right? Okay, together guys? Something like that, right? So yit minus 2 correlation with this is minus sigma square y. What about yit minus 3? That is going to be lambda times minus lambda times sigma square y. T minus 4 minus lambda square times sigma square y. Now lambda, what is lambda here? Lambda is this persistence parameter. What value should that have? You guys have not done time series here, but you have done time series at undergrad level, right? So you know that for stationarity conditions, well, which need to hold here anyway, lambda should be between minus 1 and 1, all right? But in particular, for this to make sense in an economic context, lambda should really be between 0 and 1, right? Okay? Otherwise, you have very bad kind of dynamics, right? Oscillating dynamics. Okay? So, what about lambda square? Lambda square is going to be smaller, lambda cube is going to be even smaller, so on and so forth. So, you can go on accumulating, instruments like this. However, the instruments start becoming weaker the further you go back into the past. So, you start having a weak instruments problem. Okay, so the longer lags will be weaker instruments. So let us take an example and see what happens. Suppose we have t equal to 6. Okay, that's reasonable, right? In many household surveys, you will have between 5 and 8 rounds, right? So t equal to 6 is reasonable. What about the first period? Well, the first period's data is useless for us because we cannot take differences. We cannot do differencing. Okay, we can do differencing for second period. Okay, We can do differencing, but we have no instruments. So really, we can start using data from period t equal to 3. So we have lost 2 observations, at least. And if we follow Anderson-Chow and take several of these lags, we are going to lose even more observations. So this is obviously not efficient, right? So we are not using the full information, right? So we are losing a lot. Okay? So we can't use this one because the first available instrument, this one does not exist. We can't use this either, although this is available. The second instrument isn't available, and we can't use this one because the third instrument is not available. So if we are using 3 lags like this, then we have only 2 observations that we can use. Okay, so that is a huge cost. But you get the idea, right? So that is what Anderson-Chow suggested. Now, income Arellano bond, well, really, that is what this estimator is known as. However, this estimator was discovered before Arellano and bond. Okay? So I think one should give appropriate credit to Horziakin, Nevy, and Rosen. 1988, they opted this estimator. Few years before Arellano and bond. Okay? Arellano and bond formalized it in a particular way. Okay? Right. So what do? They address this problem by creating different sets of instruments for each period. So think of the following. So you are writing down your model for different periods with different instrument set, depending on what instruments are available, right? For t equal to 3, you have only 1 instrument available. For t equal to 4, you have 2 available. For t equal to 5, you have 3 available. That's not a problem, right? This, we know how to do GMM in that setting, right? So there will be multiple sets of instruments for each period. Okay. So these are always valid instruments because they are all lagged at least twice, right? But these instruments can be weak. Okay. All right. So how does this work? For t equal to 3 through t, you can use these instruments, these moment conditions. For 4 to t, you can use these moment conditions, and so on and so forth. For the final one, you just have this moment condition. Right? So now, for our case, t equal to 6, we can use 4 observations now. All right? So that is the advantage. How many orthogonality conditions are there? See, it's going on multiplying, right? So 4 plus 3 plus 2 plus 1, 10. Okay, a lot of orthogonality conditions. Okay? Remember that these are not the only orthogonality conditions. There are also orthogonality conditions from the regressors, exogenous regressors, right? So there are a lot here. Okay? Okay, so basically what we do, we try to estimate this in first difference form. First of all, we take first differences, then we create different instruments for each period, okay? And then we combine these instrument sets in the form of a Z matrix like this, large Z matrix, okay? You can see what we are doing here. So this is the instrument for period 3, right? And for period 4, we have 2, and so on and so forth, right? This is going to go on expanding. Not a problem, right? Okay, so we know how to do GMM. There is an extended lab exercise for tomorrow's lab. We won't have time to cover all of this, where you do this by hand and do the GMM by hand, right? But we are not going to do that tomorrow. We're just going to use status commands. Don't have that much time, okay? But it is instructive to do it, because then you know that, there's no magic happening. It's not like a black box. You can obtain your own estimates. You can put in your own instruments sometimes, and put it, and you might find that useful, right? So I'll make that available at some point. Okay. Right. So how do you estimate? IVGMM, simple. You can use one-step inefficient IV, two-step feasible efficient GMM, etc. Right, and the most common choice of for S is cluster robust, heteroscedasticity consistent estimator. Why? See, one thing which is important here is that, okay, it's easiest to see here. So this we have seen for first differencing anyway. Remember that the error term is actually serially correlated. Okay, so the same problem is going to remain here, right? Okay. What do we do? So this is HENR and Arellano bond. The total number of orthogonality conditions just from the these instruments straight away is TT minus 1 by 2. This can grow quickly. For T equal to 20, we'll have 190 orthogonality conditions. Is that good? Is that bad? Well, first of all, it is good to have over identification, right? So because without over identification, we cannot do the J test. So we cannot know whether our moment conditions are valid. But if you have a large number of instruments, particularly if some of these instruments are weak, then that is a problem, right? Because IV anyway produces bias estimators, so you are accumulating bias, and how much benefit you are getting by addressing endogeneity rather than accumulating bias is a question that has to ask of the data, right? In many conditions it might be pretty bad. Okay, so the bias of the IVGMM estimator is increasing in the number of over-identified restrictions, so it may not be advisable to use all your moment conditions, even if you have them, right? Because of weak instruments problem. Okay, how do we choose these instruments appropriately? Well, there are methods of doing that, but one has to be also careful of multiple testing problems, right? So if you, for example, it's the same problem everywhere. You have seen this in lasso as well. So if you have 1,000 variables, you're doing one by one, you are testing so many times, just randomly some of those are going to become significant, right? So you have to be careful about that, right? Okay. So there are going to be two standard specification tests here. One is Hansen-Sargan. That is straightforward, right? So we know we need to do. There are a large number of moment conditions here. So we need to check the validity of these moment conditions. Usual interpretation, a word of caution I've said, the J test may not have power to detect violations of orthogonality conditions, especially if the estimation uses lots of them. Right? So power will be lacking, okay? But maybe you can bypass that by having larger sample sizes. Okay, obviously this is important, right? In some ways, large number of instruments is good because it offers over-identified restrictions which we can test. It offers some cover against weak instruments. But we suspect weak instruments problems here as well. So I'm encouraging you to think about what is the correlation between YIT minus 2 and this endogenous regressor, and then go back further in the past. So the correlations will reduce as you go further into the past. All right? Okay, that's one thing. Second thing, what does the J test tell us? Okay, so a small J test value, well, what is J test doing? It is comparing the estimates for different moment conditions, right? Conceptually, right? If you had one endogenous variable and two instruments for that, what is the J test going to do? It is going to use the first instrument first, obtain an estimator. Use the second instrument then, obtain another estimator, and it's going to do a difference between these two. When is this difference small? Well, of course this difference is small if both the instruments are valid. But this difference is also small if both the instruments are equally invalid. Okay? So we have seen this earlier, that nice principle of accumulating instruments is not to use the same principle to accumulate them, right? Find them from different sources, different kinds of reasoning, right? But that is not what we are doing here. We are using the same principle here, right? Looking into the lagged levels, to find instruments for a difference, right? And so there will be a confirmation bias in that, right? Okay, so one has to treat this with caution. Okay. So that obviously raises problems for interpretation. It also makes it very easy to ask questions in exams, right? Okay, because, all right, okay. Serial correlation, right, why do we care? Well, there's going to be first order serial correlation here, right? But under the assumptions of the model, there should not be second order serial correlation and onwards, right? So you test for second order serial correlation. Here, the standard test is the one by Erlang bond. Okay? So if second order serial correlation is present, it is a problem because that will invalidate the use of YIT minus 2 as an instrument. Okay? So that's very important. Okay, now let us do a thought experiment here, right? Okay. Suppose, okay, let me go back all the way. Okay, here. Suppose we had two lags. So we also have plus theta yi t minus 2. What happens now? So you are first differencing that, okay? You are going to have two such terms on the right hand side. Guys together? Okay? What is the first valid instrument?
T minus 4.
Well, actually T minus 3. Here the first valid instrument was T minus 2. If you have two of these, so the second term is going to become, like after differencing, that is going to become plus theta yi t minus 2 minus yi t minus 3. So t minus 3, yi t minus 3 is an instrument here, right? So t minus 3 onwards, okay? Right, okay. What about the error term? What order of autocorrelation should it have? So we know that in this model, this was autocorrelated of first order, right? Okay, but second order autocorrelation should be 0. If we had two lags, then there will be autocorrelation of second order, right? And third order should be 0. Okay? So be careful about that. Okay, here this will have first order autocorrelation but not second order autocorrelation. If second order autocorrelation is present, of course it invalidates the use of this. But if you had multiple lags in your model, then higher order autocorrelations need to be tested as well. Okay. I do not remember how I have set this up in your labs, but we'll figure out tomorrow. But the typical example here, the classic example, is one which comes from Nickel again, Nickel and Laird, right? where there are two lags. It is a employment labor demand equation with two lags on the right hand side. So one has to be careful, right? So then you have to test appropriate orders. Okay. Anyway, why is this important? Okay, so to make sure we have the dynamics right, and so on. Simple? Okay, the rest of the slides are there, and they are there for a purpose, but I am not covering them in the lectures. All right, but they show you how to make all the transformations. All right, so if you have doubt about any of these slides in the main lecture notes, go back here and check how that is used in the matrix development. Okay, it is all step to step is very simple, but there's a lot of detail here. Okay, and your JT matrix is defined here, so on and so forth. So those things are there. And then how do you write down the group means transformation in terms of matrices and so on. So if you are programming, then you will need those things. Okay, but that is a detail that I did not want to cover in the lectures. If it helps you to illustrate a point, make use of it. You know, kind of different people are different, right? Some people look at an equation and can explain it better. Some people can look at a matrix and explain it better. You know, so there are different skills. Okay, so people come with different skill sets. Some people find, working with matrices easier. Okay, they can figure out straight away what is annihilating, what is idempotent, so on and so forth. Different people are different, right? So there are different skills. Okay, but there won't be a question saying, well, show this is equal to that, and that kind of stuff, right? That you know anyway, right? The things that you have to commit to heart are right at the beginning, right? Section C and D, they're more interpretive. Okay. Yeah, I'm not going to go into those details. Right, questions? Panel data? All done? So, sorry. Actually, let me. Oh, I'm going crazy. I changed the slide on my laptop, yeah? Okay. And then I looked back and found that that is not being displayed, right? Okay. So, these are the estimators that we have looked at, okay? So, these are the panel data estimators, so back to there. All of these we are interpreting as GMM. Why are we doing this? This is somewhat new, so this is not there in the books, okay? So, but the reason we are doing it is because we think that that is a nice way to look at these things, to compare different estimators, and you can compare them on the basis of what moment conditions we put into them. Okay, so that's the idea. Okay, short break, and then we'll move into identification, okay? Okay, guys. So you guys have been doing GMM for a while now, so you are comfortable with identification, but these slides go a bit beyond, and we will see where it goes beyond, right? So you have a fair idea about identification already. We'll do a bit beyond. Okay. So far we have been focusing on the order condition, right? What is the order condition? So how many instruments do you need? All right. What are the adequate moments for those, and so on. However, we have not focused on the rank condition, and the rank condition is about the information content of these instruments. All right. So now we are going to focus on the rank condition, and some interesting things start happening. So why do we need the rank condition? Structural versus reduced form. Okay, relationship between reduced form for endogenous regressors and the rank condition. Then we will do testing for under-identification, testing for weak identification, and weak identification robust inference. Okay. Okay. The discussion in Stokkan-Watson and Hayashi are brief here. Okay, so where we are drawing from is largely Hansen's book. Okay, and for the routine data implementation, this one is a very famous program, right? So it's a very well cited paper by Mark, Kidbaum, and Steve Stillman, right? And there's a Stata add-in, weak IV, which has discussions of this. This is now in the main structure of Stata. Advanced readings. This is a very famous paper, very important paper, Bound, Jaeger, and Baker. I'm going to come back to this in a little bit. Okay, and we are actually making use of a little bit of Chris Hansen's work. So particularly this paper. This was actually published in Economics Letters. But what was the Economics Letters publishers? 5 or 6 page papers, right? So that is very concise and hard to understand. So we refer to the original working paper version. Okay? And before as well. So these are all classic examples. Okay. Key terms, I would like you to focus on the first 3, first of all, the structural form, the reduced form, and the rank condition. And then we'll go on from there. Okay. So back to what are valid instruments? What do we need of the valid instruments? So we understand assumption 3.3, weak exogeneity well. Okay, so this is what we have been focusing on so far, right? We have somewhat ignored the rank condition, but which was also there all of the time. Essentially what it says is that there is enough information in the IVs to identify all your structural parameters. All right? So that is about the rank. So this guy, sigma ZX, is a full column rank. So the rank has to be K. Okay. So previously we have focused on what happens when weak exogeneity fails. Now in this lecture we are going to focus on what happens when the rank condition fails. Okay. So this was our proof of consistency. So this was our consistency results for the GMM estimator. We had this consistency result. right? Where do we have a problem with the rank condition? Well, this guy here. Okay? Why? You see, there is a ZX here as well. But that is not a huge problem. It is a huge problem here. Why? Because we are inverting it. Okay? So that is why we need the rank condition there. Okay? If this is a full rank, full column rank, then this inversion will work fine. This will also be fine. This will have a finite, nice limit, right? But the bigger important problem is the first one. So what was this guy? We have seen this earlier. So the probability limit of this is the probability limit. We can take each of these terms separately and take the inverse. Okay? And the probability limit of this is sigma zx prime. And this is sigma zx and this is w. So this is like, sort of like the inner product of this covariance matrix, right? And that has to be full rank. So line C is where the proof will fail, right? Okay. W is positive definite, so it has rank L, so that is not a problem. But the matrix product requires the rank of this guy to be adequate, right? If we do not have adequate rank there, then we are going to have a problem. So essentially, what is the nature of the problem? The nature of the problem is that this thing cannot be inverted, right? So there's no inverse of that stuff. Okay. Okay. So if you have a simplified model now, then the intuition is quite clear as to what is going on. So we have no exogenous regressors. You have one endogenous regressor here and one excluded instrument. So the model is exactly identified. Okay, in this case, GMM is the same as IV. And this is our IV estimator, and the probability limit of this beta hat IV minus beta, this should be 0, right, is this guy here. Okay? Earlier we were focusing on this. Of course, this thing is not 0 if this is not 0, right? However, now notice what happens if we cannot think of this guy as an appropriate thing. So if this guy has, there's no rank. This has rank 0. Okay, so that is going to create the problem here. Okay, so weak externality means the numerator is 0. That isn't enough. We need the rank condition to ensure that this guy is not 0. So that we need now. Okay, as well. Okay. If this fails, then this one will be 0. So we do not know what the probability limit is. We cannot have that. Intuitively clear? Okay, so that is the problem that we are facing. So that is the problem that we will be discussing now. Okay. Notations, once again, this is a reminder of what we have done earlier. We have K1 exogenous regressors. Now we are generalizing to the general case, K2 endogenous regressors, L1 included instruments and L2 excluded instruments. Okay, so these exogenous regressors and the number of included instruments, the number is the same, so L1 equal to K1, so this is all repetition of what we have done earlier. So the order condition is not enough, okay, So the order condition, what does it do? It just counts columns of a matrix, whether you have adequately many instruments, but it doesn't focus on the information content of those instruments. A rank condition is necessary. So order condition is necessary for this rank to be k, but it is not sufficient. So we need to do something more. You will have under identification. If this rank is less than k, we'll have we'll have identification if this rank is equal to k. And that is what we need to ensure. Okay. So some more terminology. This is our structural form. What do we mean by this structural form? We essentially mean that these betas here have structural interpretation. Okay? What is the reduced form now? Reduced form is writing down each of the variables here, right? In particular for the endogenous dependent variable here, as a function of the instruments, which are purely exogenous. There are going to be coefficients there in that equation, but these coefficients do not have an economic interpretation. So that is why these are reduced form, but they are estimable. Why? Because the instruments themselves are exogenous. So you can regress them, but you do not have any interpretation for those. Okay? So we write down equations, one for each endogenous variable, yi and all the x2i's. So all of those are endogenous here in this model. Okay? With endogenous variables on the left hand side and all the exogenous variables on the right hand side. For yi, for example, this is the equation. Now this, what are these pi zeros? Nothing, means they have no interpretation. But you can do the regression. Why? Because they are exogenous. Okay, so they are going to be tools. So they can be estimated by OLS. Sometimes they can have interpretation, but usually not. What we are really interested in is in this guy beta, right? Not in these pi zeros. Okay, so this is the reduced form for the endogenous dependent variable. Likewise, we are going to have reduced forms for all the other endogenous variables. Right? Each thing which is endogenous has an equation. Okay? And in that equation on the right hand side you have all the instruments. Everything that is exogenous. So for all the others, we are going to compactly write them down like this. Okay, just combine them as a column vector, right? All the other endogenous regressors. In matrix form, that is x2 equal to z pi plus b. What are these pi's? Whenever you see pi in this lecture from now on, you are thinking that is reduced form coefficients. That doesn't have structural interpretation. Whenever you see beta, that has structural interpretation. Okay? So these equations are sometimes called first stage equations. Why? They are like two-stage least squares, right? What do you do in the first stage of two-stage least squares? You take the endogenous variables and regress them on all the instruments or all the exogenous variables, right? That first stage has no economic interpretation at all, but it is a regression that you can do. Why? Because everything on the right hand side is exogenous. So these are called first stage equations. Why? Because they are the first stage if you are doing IV in the old fashioned two-stage least squares way. Okay? Right. For the kth regressor, it is like this, and we have combined this together in this way. It is a compact way of writing down k2 different equations. Okay, the kth column of this x2 prime I is a scalar. Okay, it's the ith observation I of the kth endogenous regressor, right? Zi is simply a data row of instruments. What are the instruments here? All the exogenous regressors plus all the excluded instruments. Everything is combined together, right? Okay. So this is our matrix form then, right? So this is like a system of equations really. That's all that there is to it. In Stata, this form is called a wide form, okay, of writing down equations. Okay, that is typically what we use for three-stage least squares and seemingly unrelated regressions. That's an aside. Okay. Now we are going to start partitioning or Z, like we did before. So what are the regressors and what are the excluded instruments? So we partition Zi into the included instruments, exogenous regressors, and the excluded instruments. And correspondingly, we are going to also partition this pi matrix conformably. Okay? So having partitioned that, now what have we done is that we have written this out into two different parts, right? So this one here, they are your included instruments. So these are regressors in your original model, right? And these are the excluded instruments in your original model. Okay, so we are just spreading this out into two parts. Okay? So in matrix form, we can once again write this in the following way. Right? This pi 1 is L1 by K2, this pi 2 is L2 by K2. So far so good? Okay? Where is the interesting thing going to be? Lie. It is going to lie in the pi 2. If we are interested in the rank, where should we be looking? We will be looking here, right? Okay, that is where the interesting things will lie. So I'll come to that in a few minutes. Right. So this is our format now, or the first stage equations, reduced form equations. Right. So we can test whether the rank condition is satisfied by estimating these reduced form equations using OLS and testing the rank of this guy, right? Simple. Okay, that is what we have been trying to do all along. Okay? Is everybody together so far? What have we done? We have taken all the endogenous regressors and written down an equation for each of those, first stage equation, as a function of the included instruments and the excluded instruments. The important thing here is the rank corresponding to the excluded instruments, right? So we are trying to find out whether the excluded instruments have enough information. Okay, so that is what we are trying to do. So what are we testing? We are testing whether this pi 2 is of full column rank, or rank of pi 2 is equal to K2. All right? Right. So if rank pi is equal to K, all of the K coefficients beta are identified. If rank of pi 2 is equal to K2, all of the K2 coefficients beta 2 are identified. So how do we proceed? Well, we are going to do our standard FWL here, right? Or think in terms of doing FWL. So suppose we were estimating the K2 reduced form equations using OLS, right? FWL, what does it tell us? That the estimated reduced form coefficients, this guy, obtained from OLS will be the same whether we estimate pi2 hat as part of the full pi hat or we estimate it separately. Okay, or we partial out all the included instruments, the Z1 guys here, right? Okay, and then do the estimation. So it doesn't matter which way we do it. Okay, so we'll get the same pi2 hat. So either way we are fine. So typically we will be just doing the full form here. Okay. What is the problem? The problem is going to arise if rank pi2 is less than k2. Then the model is under-identified. So you may have sufficiently many instruments there, but these instruments do not have adequate information to identify all the structural parameters. Okay? So beta 2 then cannot be appropriately estimated. Right. This problem actually is a fairly old problem, right? So it goes back to the 1950s where Anderson did some fairly important work, and we are going to come back to his name again in a little bit when we go into this a little bit. The problem is a bit more intricate. Okay, we have gone into data, and maybe we have found that, well, we have estimated this guy pi2, that is very easy to estimate, right? It's just OLS. And we find that that is full rank. But it may be full rank, but it may be very close to being under-identified. Well, first of all, how do we know that it is full rank in the first place? So we are going to do a test, right? It is a statistical test about unknown parameters in the population. So we can never be sure, right? Okay, so there's uncertainty there. This notion of uncertainty is actually very important here, because even if the rank was K2, of pi2 was K2, but pi2 was very small, we are never quite sure how much identification we are getting. That is the problem of weak instruments. Alright? So it may be full rank, but the information content is so tiny that, kind of we have to accumulate enormous amount of data to try and get something meaningful out of it. So that is the problem of weak identification, which was identified in a series of papers in the 1990s. Okay? Yes?
So what do you mean by small pi2? It's a matrix. What's a small matrix?
What do I mean by small is that the off-diagonal, okay, so the diagonal elements are too small. Or, the matrix, the elements are so small that we are not sure whether they are 0 or not.
Okay.
So it needs to be full column rank, right? And if we partial it somehow, maybe one column has values which are very close to 0. We are not sure whether that is actually a full rank. That is the problem of weak identification. Okay? Got it, guys? So basically what is happening is that there is information here. But we are not sure whether this information is just because of random variation in the sample of this, or this information actually relates to the population, whether there is adequate information in the population. That is the problem that we are grappling with. Okay? So in this case, we will have finite sample bias problems on the way to infinity and modified asymptotic framework. Not covered in detail in this lecture, but covered somewhat. So we are coming to that. Okay. First of all, let us look at the first part, under identification. How do we know that the rank is, how do we test that the rank is full? Okay, so let us take a simple case first of one endogenous regressor like we have done before. Okay, so what does the reduced form look like? The reduced form equation is just a single regressor, right? So just a single one here, right? X2i. And this X2i and Vi are now scalars. On the right hand side, we have the other regressors which are exogenous plus all the instruments. And there are multiple instruments here, potentially. Okay, there needs to be at least one. Okay, so this is like the first stage of a two-stage least squares regression model, right, or regression estimation. So what is pi2 here? Pi2 is a L2 by 1 vector. Pi2 is a L2 by 1 vector, L2 being the number of excluded instruments. What rank does pi2 need to have? Well, pi2 can have maximum rank 1, right, because it has a single column and it needs to have rank 1. Okay? So, what does pi2 need to be? Pi2 needs to be non-zero. If pi2 is 0, then you do not have identification, right? So you are under-identified. Together, everyone? Right? The rank of pi2 being 1 means that pi2 is not 0, right? In this case, it's just a single column. Okay? So not full rank means rank of pi2 is 0. Only way this can happen is if pi2 is equal to 0. So, what is the test of under-identification? Estimate the equation using OLS and test whether this guy is equal to 0. How do we do that? This is very simple to do. This is just OLS. Okay. What test do you use? Okay. It is only part of this, right? So we are not interested in this part. We are only interested in this part. How do you do that? That's the standard F test. Yeah?
Are you testing that both of them are equal to 0?
No. I'm just testing whether this guy is equal to 0.
Well, then wouldn't that just be a t-test? Why would that be a joint? Yeah.
Well, there are several of instruments. All right, there are several instruments. Potentially, right? There's a single endogenous regressor, but excluded instruments are several, right? Okay, potentially. So we need to test that all of them are 0. All right, that is an F test. Testing this guy is the same as doing FWL, right? Partialing out all the exogenous regressors and doing this test, right? The F statistic for both of these tests will be the same. That is the reason why when you did two-stage least squares, probably your lecturer always told you, look at the F statistic and make sure that it is at least 10. That is the Bound, Jaeger and Becker paper, JASA paper. Alright, so that is where this comes from. Okay? But we are going to do this more appropriately, right? Okay, but that is always a first test, right? So when you do the first stage, F statistic, is it 10? Why do we do that? Well, precisely for this reason. Okay? Right. So we're going to reject this. If we reject this, then the rank condition is satisfied and beta 2 is unidentified. If we fail to reject this, we are not sure, right? Okay, so it is unidentified. But the moment you are doing a testing, of course, there's uncertainty here, right? Okay, so the usual test statistic is a WALDF, or chi-square test statistic, of the joint significance of the excluded instruments, Z2i. That is nice because now we can make this robust to heteroscedasticity and serial correlation with corresponding robust WALD statistics. For the asymptotic variance, we can use heteroscedasticity consistent or cluster robust, etc. Right. Suppose now we had more. Okay. Now it's going to be a simple extension, right? Okay. Now we cannot just look at the first stage of statistics. Is that clear to everyone? Or do I need to go into the logic? If there was a single regressor, that was fine. Endogenous regressor, that was fine. Right? If you have multiple, then you have to test it jointly, right? Okay? Each column might be non-zero, but still the rank can be deficient, right? The first column can be, what was our, we are using pi, right? The first column was pi 2 1, pi 2, well, how many over you have k2, right? And the second column is, sorry, I don't care how many are there. And the next one is pi 2 2, pi 2 2. What is the rank of this? These elements are all the same. These elements are all the same. Rank is 1, right? So that is rank deficient. If you do the F statistic, you can check whether this is non-zero. You can check whether this is non-zero, but that does not suffice. Right? You can still be rank deficient. So we need to do this together. Okay? Right. So that is explained in another way here. Suppose K2 and L2 are 10, but 9 of your instruments came out of a random number generator. You really have information only from one IB. The rest do not matter. They are just rubbish. Okay? Right. So this will be correlated with 10 of your X2Is, right? But you can't identify 10 parameters with only one instrument. Okay? So that's the point. What do you do then? Well, there are two cases. You may be interested in all coefficients beta 2 on the endogenous regressors, or you may be interested in just one of those. So what you want to do depends on that. Okay. Well, suppose you are interested in all the coefficients, then you need to test the rank of this directly. Okay. There are various tests available here. First of all, Anderson. This is from the 1950s. Okay, the canonical correlations test. that requires classical assumptions of homoscedasticity and independence. Okay. Then there have been better developments, more recent developments. Craig-Donald test, that is a word test that also requires homoscedasticity and independence assumptions. The critical values are a bit interesting, let's put it this way. And then there's the more common one these days is the Kleibergen-Papp RK statistic. Okay, so this generalizes to the non-classical case, hence you can use any kind of covariance matrix, right, as appropriate. For all of these, what is your null hypothesis? Your null hypothesis is the rank of pi 2 is k2 minus 1. So null hypothesis is that pi 2 is rank deficient. All right? That is why this is called a test for under-identification. If your rank was k2 minus 1, you are under-identified. Okay? So in large samples, the test statistic is distributed as chi-square. Okay? If you have a rejection, that means your rank condition is satisfied and beta 2 is identified. Okay? Nice and simple. I'm not going into details here, right? These test statistics, these things look quite horrendous, and they have tables. You have to use tables and so on and so forth, but they are there in Stata, right? So Stata will do it for you. Okay. Case 2, yes.
For the rank test, still, would you always do a one-sided test, one-tailed test? Surely you also need to test for lower ranks than K2 minus 1. We're only interested in case whether it would be higher than this.
Yeah, right. So basically, it says that your rank, the hypothesis, null hypothesis is that rank is k2 minus 1, but suppose the rank was even lower than that, then this test is consistent. All right? We cannot say more than that, but at least it is consistent. So we are doing fine here. So if we can reject on the one-tailed way, then we can ensure that this is actually not rank deficient. Okay? Right. But that begs questions because we have not covered consistent testing, right? So, but what is a consistent test that we have considered? I've not really talked about it. But the likelihood ratio test is consistent. Okay, so this is a likelihood ratio test. So that's why. Yeah.
In regards to K2, what's the rank of K2? Yeah.
What is the?
What's the rank of K2?
No. K2 is just the number of, what was it? The number of endogenous regressors. No, just a minute. What is, yes. No, the excluded instrument, sorry. It's the number of excluded instruments. So this is K2. K2 here is 2. Okay? It's the number of excluded instruments.
So it doesn't pertain to the L2 and K2 though?
Yes, it does.
Because the one defined at the start. Sorry, the one defined at the start is that it was.
Oh, sorry.
It was endogenous regressors.
No, sorry. It is the number of endogenous regressors. You're absolutely right. So this is the number of endogenous regressors, and what rank do you need to have of your pi 2? That is the same as the number of endogenous regressors. So that is what you're testing. Yes, that is right. Yeah. Yes, please. Yeah.
Why you say if rank of Part2 is less than k2 minus 1, we are rank consistent?
Okay, if the rank is less than, so the rank has to be K2, right? Otherwise we cannot identify these parameters, corresponding beta parameters, right? Okay, whenever the rank is less, that means the information content is less. Okay, so where is it? So this condition will violate in that case.
No, but my confusion is that why the non-hypothesis is to test K2 minus 1, not K2.
Oh, okay. Right. That is according to convenience. Okay? So, whether you place your null hypothesis here or you place your null hypothesis at K2, okay, you might get a different test for your null hypothesis as K2, but rank is K2, all right? That would be a valid test as well. In this particular test, the null hypothesis is rank of pi 2 is K2 minus 1, and it is a one-sided test. This test suffices, right? Yeah, one-tailed test, right? So this suffices, right? So if I can test whether the rank is K2 minus 1 and reject it in favor of rank larger than that, then I'm fine. Means one could have a different test, potentially, the rank of this is K2, and reject it on the lower side. That would be a different test. Okay? But for this test, this is how you do it. Okay, so that is the reason why it is called an under-identification test. There are other tests which are tests of identification, right? Yes?
So we'll reject their H0 only when rank is bigger than K2 minus 1.
If we reject, that means rank is larger than K2 minus 1. How much larger can it be? It can only be K2. Right? And that is exactly what we want. Okay? So rejecting this is good news. Okay? Right. Now, suppose we were interested in a single coefficient beta 2. Not the whole guy, but a single coefficient beta 2. Okay, so how would we proceed? Now we would do a lot of partialing out, right? So Angus and Pishke, they propose a first stage chi-square or F statistic for the coefficient of interest. Okay? You obtain first stage fitted values of the remaining endogenous regressors, then you partial them out on the basis of this, and this is like a first stage regression. Okay, so everything that is you are not interested in, they are partialed out, and you are doing bound Jaeger-Becker, basically, all right? So that generates a chi-square or F statistic for testing whether the particular coefficient of interest is identified. One specific case of this, a very interesting one, is by Sanderson and Windmeyer. Okay, I'm going to come back to this a bit later in the context of the Anderson-Rubin test, so this should be an AR. No, sorry, this is the Angus-Pishke test. I'm going to come back to this. Yeah. Okay. So far so good with under-identification, right? We had divided the problem into two parts. So how are we discussing this? First of all, we are discussing under-identification. We have discussed under-identification. Within that, we have discussed two cases. One is we are interested in the whole of the beta 2, and one is we are interested in just one of the coefficients of beta 2. All right? Now we will go back to weak identification. I will spend quite some time on that. Okay, so I'm going to set down concepts in a little bit and then proceed from there. Okay. Okay, so we have rejected under identification. Big deal, because our instruments may be weak. So we need to know whether they are providing sufficient information. Okay? So we need to do, so under identification at conventional significance levels is not going to be enough. So we're going to try and find out whether we have weak identification. So now we go into weak identification. In fact, as we have pointed out, so discussed this earlier, this actually comes from Han and Hausman. The finite sample bias of the IV estimator increases as the correlation between X2I and Z2I falls. That is intuitively quite intuitive, right? If Z is not correlated with X, right? If these are the Z are the excluded instruments, they are not sufficiently correlated with the endogenous variables, then of course your bias of IV estimator will increase, and that is precisely the problem, right? IV has a bias, and this bias will increase if you do not have strong identification. Here is this famous Baker paper. They re-examined the wage equation study by Angrist and Kruger with a sample of over 300,000 individuals, and there are still substantial identification problems. All right, and finite sample bias. So even if your sample size is very large, you can have substantial bias if these two guys are not sufficiently strongly correlated. Okay, we have verified the rank condition, but that is not quite sufficient. Okay. So remember that the finite sample bias is also increasing in the number of excluded instruments, right? So, okay, so one lesson here is do not use too many instruments. What about Arellano bond? Well, I leave you guys to think about it. Okay, but Arellano bond is not the only one. Actually, the typical one that people use is Blundell bond, which has lot more instruments. Okay, if you go back to your past exam papers, you will find questions on Blundell bond as well. So have a look at that. Maybe there is one in your next tutorial as well. I don't remember. I'll check. Anyway, okay. Steger and Stock, Econometrics in 1997, they proposed an asymptotic framework to deal with weak instruments, and that is going to be important for both this and weak instrument robust inference that we are going to consider a bit later. So what is this asymptotic setting? Asymptotic setting is this pi2 becomes smaller as n increases. So in finite samples, pi2 can still have full rank, but as n goes to infinity, the information is getting smaller and smaller. So you have an instrument which is very spatial, which is like giving you a little bit of bite now, but as you go on to larger and larger samples, that is not going to have an effect. Think of it that way. Okay? So this is zero in the limit. So Harsh has a brief discussion. Here the asymptotic setting is different. It is called local to zero asymptotics. Well, so get limiting distributions n goes to infinity, but we are fixing the amount of information that the instrument Z has about the endogenous regressor X2I. Okay. So essentially that is local to zero asymptotics. The other way of looking at it is that it lets us assess the normal approximation of the IV estimator, essentially. Okay? Let us see how this works. What is the standard test statistic for weak identification? Well, that is the same F statistic for under identification. The two are exactly the same. Okay? In the case of a single endogenous regressor. And Craig and Donald then extend this to the K2 more than one, so more than one endogenous regressor case. Both of these have non-standard critical values. Okay? Because we are dealing with IV here, and that is biased. Okay, so they have non-standard critical values, but they are tabulated elsewhere. And your favorite friend, Stata, has a table inside. It looks up values. Okay, so right. Steger and Stock rule of thumb is for IV to SLS. A for Craig-Donald should be at least 10. For Stock and Yogo, they do extensive Monte Carlo experiments and tabulate the critical values for, I think, up to 3 endogenous regressors. Okay? That doesn't help in my work, my own work. Because in my own work, the number of endogenous regressors are typically n in panel settings where there are n endogenous regressors, right? So it doesn't really help. So I have to do other things. But this is the standard one, okay? So what do you do if you have heteroscedasticity, serial correlation, etc.? It's not quite known. Okay, so things are getting developed there. There's one important paper by Monteloli and Pfluger in Journal of Business and Economic Statistics. So that's fairly recent, 2013. What to do for K2 greater than 1 is also an area of current research, as I said, particularly if K2 is increasing with n. All right, so that is an area of work as well, and also pointed out some things here, Sanders and Weinmeier, for example. 2013 was their working paper version, 2015 is the published version. So what is the null hypothesis here? Instruments are weak. Okay, earlier the null hypothesis was that there was under-identification. Okay, sort of similar, right? So the instruments are weak. So this is not usually an interesting hypothesis in its own right. Why? Because if you are using this test repeatedly as a pretest, you have large pretest bias. What do I mean by that? Where would you like to use such a test? You have one endogenous regressor, you have 100 different instruments, potential instruments, okay, right? And you are trying to test whether these instruments are weak, okay? By doing this repeatedly, and then you pick up one which, rejects weak instrument null hypothesis. Wow, okay, but you might have just rejected that by chance. So using this as a pretest is going to generate even more bias in your IV. Okay, so that's the problem. Okay, so that's a very important paper here, which is somewhat previous to this. So Horwood, Bush, and Wilcox in a macro setting, which is quite interesting. Okay. So we are going to give up on this. Okay, so there are weak identification tests, but what we are going to do now is to give up on this weak identification test and rather think of the problem as weak identification robust inference. Can we make our inference robust to the potential of weak identification? Okay? So I'm going to briefly jot down, briefly, make a small drawing on the board, all right, to illustrate the problem, and then we are going to continue the discussion after lunch. Okay? So I've already tested for under identification, all right, and you have rejected the null hypothesis that rank of Part2 is K2 minus 1. So I rejected this. Good. But you do not know how strong the identification is. You have rejected this at 5% level, so you are admitting some possibility directly that actually your inference might be wrong. So admitting uncertainty. Suppose this null hypothesis holds, then your beta 2 is not identified, right? But you are not sure. Okay? So if beta 2 was identified, then if you were trying to do now a test of beta 2 is equal to 0, your power of the test would look like something like this, right? This is the beta 2 value. You guys have seen power functions, right, earlier? Okay, so it looks like something like this. So that is a typical case for point identification. But you are sort of unsure. What have I drawn this line? I've drawn this line at 95%, right? Okay, and your 95% confidence interval then is this guy. You guys are comfortable with these things, right? Okay, so there's the power of the test. Okay? So your 95% confidence interval is like this. There used to be another different colored pen that has vanished. Okay, let me just do with this. But now you're not so sure. So what do you mean by not being so sure? You can mean something like this. So now, if Part2 were actually lower rank, your beta 2 is not point identified, but sorry, I'm doing this slightly wrong.